welcome to the 17th lecture of optical sensors course. In the last lecture we discussed optimum configurations for LSPR sensing and also we studied fluorescence. Then we described that similar to SIRS we can have in plasmonic enhancements in fluorescence, in IR absorption, and we discussed Sierra and Ceph based sensing. We then discussed what is colorimetric sensing and then we concluded with cavity ring down absorption spectroscopy. Today we are going to discuss interference based sensors. In particular, we will discuss what is Michelson Interferometer and its applications, and then if time permits we will go to Mach-Zehnder interferometers. So, in interference you know that if you have two coherent waves and they are superimposed on each other, you will get either a maximum or a minimum. So, suppose you have an amplifier connected with two speakers and they are producing longitudinal waves. So, like sound. So, this travels in the form of compression and rarefaction. These regions where you have less dense, it is rarefaction, and so these longitudinal waves are travelling in form of compression and rarefaction, and if the waves from the speaker 1 and speaker 2, let us say they are superimposed over each other, and if they interfere constructively, then this microphone detects a loud sound. However, if they interfere destructively, the microphone detects little or no sound. So, this happens not only for longitudinal waves, but also transverse waves. So, suppose you have a wave which is travelling in x direction and it has electric field amplitude E1. Suppose you have other wave which is travelling in x direction and it has amplitude E2, and if they are superimposed over each other and say at certain position of x, and if their crest, this is now called crest and this is called trough. So, if the crest lies over crest and trough lies over trough, then you will have the amplitudes added. So, it will be E1 plus E2 here at this point. So, resultant amplitude E1 plus E2 everywhere, and if they are out of phase, say, so this is mod E1, and if they are out of phase like this, so it will be E1 minus E2. So, this is how the electric fields vary, and when these electric fields vary, then the intensity can be given by I is equal to mod E1 plus E2 square, and which becomes E1 square plus E2 square plus 2 E1 dot E2. So, these are all actually fields. So, it is like this. So, if you write it in terms of intensities, you get I is equal to I1 plus I2 plus this extra term. So, the resultant intensity is not just equal to the intensities of these two waves, but also this extra term which is the interference term. And if the intensities of the two waves which are interfering with each other are same, let us say it is I0, then I becomes equal to 4 I0 cos square delta by 2. This delta is the phase term, and if the phase difference between these two waves is say a multiple of 2 m pi, then you will have a constructive interference. If you have delta equal to 2 m plus 1 pi, then it is destructive interference. So, if you have waves which have a phase difference of 0 or 2 pi or 4 pi, then you have constructive interference. If the waves have a phase difference of pi or 3 pi, 5 pi, so odd multiples of pi, you will have destructive interference. And this phase basically can be converted in terms of the path difference, and here you can see that if you have a path difference of say lambda, then you will have constructive interference. If you have path difference of lambda by 2, you will have destructive interference. And when you have constructive interference, the maximum intensity can go up to 4 times I 0. So, suppose this term becomes 1, then you have maximum intensity can go 4 I 0. So, the maximum intensity can be not just be the sum of two intensities, but it can go to 4 times. Also the minimum can be 0, but if you write the average intensity, so this cos square, this term the average value is 1 by 2. So, average value will be 2 I 0. So, it is still okay that if they have two waves with intensities I 0 each, then the average intensity will be 2 I 0, but when you see the intensity distribution over a period of space, it is 4 I 0 at certain places and 0 at certain places. So, here we will discuss a particular case of Michelson interferometer. So, Michelson got Nobel Prize for this kind of interferometer, which we are going to discuss, and it was in 1907. 130 years after this, in 2017, these 3 people got Nobel Prize. So, see, this is a 130-year-old technique, but it is still so powerful, still so useful. We will discuss why they got this Nobel Prize, but let us see what is the basic design of a Michelson interferometer. So, here you have 2 mirrors, and this one of these mirrors can be movable, say mirror M1 and M2, and then they are kept at 90 degrees to each other. Then you have a source, and from this source what happens that you put a beam splitter in such a way that 50% light goes here and 50% light goes there. So, it is kept at 45 degrees to this source. So, half of the light goes up, half of the light goes straight. The light which goes there, say at a mirror M1 placed at a distance d1 from this beam splitter, it goes there and comes back. So, it travels 2 d1. Similarly, here it becomes 2 d2. This is the path difference. So, what happens if you see it here, you have a path difference of 2 d1 minus d2 here of the light which got reflected. So, the phase difference is related to it like 2 pi by lambda into 2 d1 minus d2. So, this was the condition. So, we can always convert it to the condition for path difference. After 130 years, they got this Nobel Prize because of detection of gravitational waves, and that is done using laser interferometer gravitational wave observatory, where you can see that this is a Michelson interferometer and each of the arms is in kilometers. So, it is again these two arms, one mirror is here, one mirror here, and 2 arms. And when gravitational wave passes through that interferometer, they will displace the mirror, they are so sensitive. So, because of this only they got this Nobel Prize, and arm length is 4 kilometers. It has displacement sensitivity of 10 to the power minus 16. Can you imagine? I mean, it is so sensitive. That is how it can detect gravitational waves. So, what happens actually when you have interference, you will have bright and dark fringes, and when we convert phase difference to path difference in the interference condition, we see that when you have this path difference integral multiples of lambda, you will have maxima. If you have odd integral multiples, then you will have minima. And the order of the fringe is given by this relation. So, 2 d by lambda is equal to m. So, if it is m is equal to 0, then it is first order film. If it is 0th order, then first order, then second order, something like that. As d is increased, new fringes appear at the center, and the existing fringes move outwards and finally move out of the field of view. So, for any value of d, the central fringe has the largest value of m. Okay. Formation of fringes in Michelson interferometer. If you have a collimated source, a source which is having a beam of light like this laser, either you see a maximum or a minimum. So, you see uniform illumination, either it will be a bright one or dark illumination, do not see any fringe. But if you have extended source like this or like this, point source or extended source, then you see fringe patterns. And if you remember the fringes for a thin film, which you might have studied in graduation courses in the first year of second year of graduation, what you see is that you will get circular fringes. So, what happens actually that you can think this setup as this. So, you have mirror M1 and M2, which is say this distance d1, this is distance d2. What happens actually that if say image of this mirror can be seen like this, and this is d1 difference d2, actually 2 times d1 difference d2. So, it is kind of a film. So, it kinds of film, and if this 2d is a m lambda, you will have maximum. If it is m plus half lambda, you have minimum. So, you are getting circular fringes like this. But if these are not exactly at 90 degree, there is slight inclination, then what will happen? You have this m2 here and m1 will be like this, the image of m1, they are not exactly perpendicular. Then you will have a wedge shape film, and this will give you straight fringes, straight line fringes. So, you will get this kind of fringes. So, depends how you adjust it. So, there are screws where you adjust the plane of the mirror, so that you get circular or this kind of fringes. Applications of Michelson interferometer. So, we know 2d cos theta is equal to m lambda. Now, if you put theta is equal to 0, we assume that there is no tilt. So, we are getting this thing. Now, one of the mirrors is moved. So, when I showed you this thing here, one of the mirrors was movable. So, it changes position. So, 2d changes. So, the path difference changes, and when the path difference changes, what will happen? That the order of the fringe will change. So, by measuring the order of the fringe, that is delta m, you can, and you know how much you moved. So, you know delta d and delta m. So, you can always estimate what is lambda. So, this way you can estimate the wavelength of light used. So, this is very useful. I will show you later that how it can be used for sensing. Suppose you have a two wavelengths which are close to each other, then you will have these two relations for these two wavelengths. So, you will have a beating pattern which will have these two terms. So, we cannot measure it, it is problem. All we can measure is the intensity. Okay. So, if lambda 1 and lambda 2 are very different, the beating will be very fast and it will be too fast to be observed. But what inferences we can draw is that we can know what is lambda 1 and lambda 2. How? If we fit some value to this and then we know what is delta d. So, what we do is that you have this curve for small delta d, for the same one you have for lambda 2 you will have different intensities and then you can have this beating. So, let us say that for lambda 1 it becomes constructive and we choose delta d in such a way that for lambda 2 it becomes destructive. So, if we solve for it, what you get is that delta lambda is equal to lambda square by 4 delta d. So, for very small wavelengths, say if the difference is very small, then we get this relation. So, suppose you have two lines, spectral lines which are very close, say by delta lambda, you can use Michelson interferometer to detect the shift in delta lambda. Now, see how it can be used for sensing. So, I told you in the beginning that when we were discussing say plasmon resonance sensor, we are plotting here lambda, and here you were plotting the intensity reflected light, and then you were getting this kind of curve. If you remember, this was for n1, this was for n2. Now, I want to measure lambda. I told you how to measure lambda. So, if you have Michelson interferometer, you can measure the wavelength of light. Okay. So, you can measure which lambda is coming. Also, you can measure this delta lambda. If they are very close, you can choose a very sensitive method. You can choose delta d in such a way. So, you have to tune delta d in such a way that you know what is delta lambda, but this happens only for very close. So, this can be used for high resolution sensors. Okay. So, I come again back to the same thing that if you have two beating frequencies, what you can do is that you simply take a Fourier transform of above equation. So, for every intensities you will have 4 pi by lambda 1, you will have intensities like this. So, from this you can know what are the lambdas present in the source, and it will not just give you lambdas, but also the corresponding intensities. It is very distinct. This is called Fourier transform spectroscopy. It is very useful technique. Let us see how. So, we will show you something called Fourier transform IR spectroscopy. Let us say that our source is in IR, and we want to determine the glucose concentration in whole blood using this technique. So, FTIR technique, what is this? You have an IR source, and this IR source is having multiple wavelengths. It is not just one wavelength, it is a broadband source, and you have a sample here in one of the arms. What will happen? You can move the reference mirror, which was this mirror, and you can have I as a function of delta d, and that will come in terms of phi naught plus omega t into d omega. So, if you solve for the Fourier transform, you can have Fourier transform of I omega t, and normalization to this gives t omega, that is a transmission with respect to omega, or absorption as a function in terms of absorption. Because you know intensities, you can always convert it to transmission or reflected absorption power. So, let us go to the background to know what is whole blood. It has 45% of cells, and 55% of it is water and dissolved solids. It is like a serum. So, clinical levels of glucose are like this, normal blood glucose is like this. So, what is the use of FTIR spectroscopy? Because in IR you have high water absorption. So, you can have this directly working for the analyte, rather you having a a receptor, and also it can be used for complex blood matrix, because the blood cells of a few microns. So, it is of the same order of magnitude of the wavelength. So, basically it is not getting scattered much. So, that is the it is considered whole blood matrix as one analyte, does not see much about the composition. So, here I have plotted the transmission spectrum of water, and for different thicknesses of the say flow cell, you can see that 25 micron, 50 micron, 200 micron flow cell like the thickness of the water column, and you can see the red, blue and black curves here, and these are the regions, the shaded ones, which are the glucose absorption curve regions. So, you can see that there is a fair match about 1000 and this wavelengths, where you can have glucose absorption, and from the FTIR spectrum you can see the peaks here to determine what are glucose concentration. So, here I show you the absorption spectrum of glucose, say for 60 millimolar concentration, and for the FTIR spectrum you can see that here for until a 2 centimeter inverse resolution you can have this kind of curve here. So, it shows you the glucose concentration. Now, if you change the glucose concentration, this will start changing the absorption. This spectrum can be simulated also if you use Lorentz oscillators. So, what you do is that you have Lorentz oscillator model of this system and then you incident on it with IR wavelength. So, that is what you can do. So, using this technique what was done is that for FTIR data and clinical data you can see that is a very fair match. So, you can use it for determination of glucose in whole blood. Optical coherence tomography. We know that in Michelson interferometer that these two beams interfere and then you get information about delta D. Now, that happens for say wavelength lambda 1. Now, if you take a polychromatic source, not exactly, but say having a small spectral range, narrow spectral range, say 30 or 50 nanometer, 30 to 50 nanometer, and for each wavelength it has a maximum at different d values. So, then what you can do is that you can do imaging using this technique. So, for each lambda you can have a depth scan. So, this way you can say have a scan of the few microns inside the thickness of the skin. Okay. So, you can do that. So, that is what called tomography, optical coherence tomography. So, you have to have a quasi coherent beam, it has to be coherent, because you know that this is the condition for having a sustained interference pattern, that you have to have coherent light sources. So, but if you have a small spectral width, you know the coherence starts decreasing. So, there is a compromise where you have this kind of light source which has partially coherent and has a small spectral width, then for each value of lambda you can have this maximum or minimum condition whatever you want to do at different thicknesses of the D. So, that is how it is used for say imaging of a sample. So, for different thicknesses it has maximum value and then you can have interference maxima, from there you can conclude how this depth profile looks like. Mach-Zehnder interferometer. In this kind of interferometer you have two mirrors and two beam splitters. So, light goes like this, you have a beam splitter which partially reflects and transmits. So, light can go from here and here, then again from this is 100% reflecting, this is say 50% reflection, and same here 100%, and here it is 50% reflection. So, what happens actually that these two beams combine here to give you the interference pattern. So, the basic principle lies same. If you have delta which is 2 m pi, then you will have constructive and then you will have maxima. If delta is 2 m plus 1 pi, you have minima. This is the condition which has to be followed here. So, if you will get a maximum when you have this phase difference, and then you can always convert it to the path difference. Now, what we do is that you can always put here a transduction mechanism. So, if you put a transduction mechanism, transducer here, and you put a sample here, the light will get modulated. So, in one of the arms, that is called sensor arm. So, suppose here you put, so this will become sensor arm and this will work as reference arm. So, light gets modulated here, this will lead to change in phase, and the phase difference here which occurred will lead to change in the intensity profile. So, by measuring the change in intensity profile, you can convert it how much change in phase occurred, and from there you can conclude that how much. So, if you remember that phase was delta phi was 2 pi by lambda d is fixed into delta n. So, if you change the refractive index by delta n, the phase will change by delta delta. That is how you measure the, and so this kind of phase change can be translated to how much change in refractive index occurred. So, that is how you use it for sensing application. It can also be used with directional sensitivity. So, suppose you have now superposition of two orthogonally polarized waves. So, it will not only change the output intensity, but also the polarization ellipse. So, here are two polarizations which are orthogonally polarized and then they are superposed. So, polarization ellipse carries two informations, one is that shape and elevation angle, or you can say phase difference and direction. So, by this way you can have a differential phase in measurements also. So, people have used this kind of things for integrated biosensors. I already told you evanescent wave sensing. So, what they did is that you have a waveguide here on a glass substrate, it has two arms, one of the arms you put a sample. So, it is a waveguide. So, it will have evanescent field here, evanescent field which interacts with the sample. You can also have 3 waveguide couplers, and if you want to go in more detail you can see this paper. So, this way you can have evanescent wave sensor using Mach-Zehender interferometer, and this can be integrated on a chip. You can have FTIR interferometers. What you do is that in one of the arms you put this prism setup, that is Kreshman configuration, right. So, the phase change of the reflected p polarized light will be given by this relation, and for measuring the phase change it is possible to use interferometry. So, the S polarized light can be used as the reference and p polarized light can be used for the measuring beam, because it is the p polarized light which is exciting surface plasmons. So, that is how you use it for SPR based interferometric sensors. So, that gives an additional level of sensitivity to it. So, it becomes even more sensitive. You can have differential phase measurement, which I already told you that now you have P and S both polarizations which are orthogonal, and by putting a Boltzmann prism here you can have P and S polarizations, and since the P phase only is altered by the SPR, this allows to remove the noise. So, sensitivity in this particular case is of the order of 10 to the power minus 8 RIU per 0.01 degrees of phase change. So, it is very sensitive. So, let us summarize this. So, we discussed today what is the interference and the basics of Michelson interferometer. Then we studied what are the applications of Michelson interferometer and how can be used for sensing, and we showed one example of Fourier transform IR sensing. So, Fourier transform spectroscopy we studied what it is, the basics, and then why we are going in IR, and then how we are using it for detection of glucose in whole blood. Then we discussed briefly what is Mach-Zehender interferometer, and also we saw how integrated biosensors on chip, and also we also discussed the differential phase measurements which are very important. So, there you use two orthogonal polarizations to make it more sensitive. Thank you.